what's happening with deep learning silicon. And it's a kind of progress report because I've been working on monitoring what's happening in the deep learning area, and most especially the deep learning silicon area, for 3 or 4 years pretty systematically. And it's an opportunity to talk both about what's the essence of deep learning down at its mathematical foundations. So you can go home and tell your high schooler that you did some real math today. And what's happening at the application level, and specifically looking at the kinds of applications in vision and in speech which are likely to drive the highest volume applications and hence be most relevant to the silicon world. But let's start with some real basics. In a sense, the core idea of deep learning is that we're going to build a pretty complex, a moderately complex mathematical model that mimics certain behaviors, selected behavior of an even more complex but hidden system. Often the hidden system in question is the human brain and all of its memory and cognitive capabilities. We're going to select out one particular capability. For example, the ability to recognize breeds of dog, or the recognition of certain phrases of speech, and train a model specifically to mimic that one dimension of it. And we do that by getting a lot of examples of both the thing we're looking for and things we're not looking for, and label them. And then we take the series of images or voice samples, run them through our model in development, and look at what we get. It starts out being a random value, but then we look at the difference between what that model produces and what the expected result is. And we nudge the coefficients of that model in the right direction in order to reduce the error. And we repeat that again and again and again. And in fact, that incremental evaluate the model, compare the results, increment the coefficients of the model is the essence of deep learning training. And it typically is a very computationally intensive task, and you might spend 10 to the 20th operations on a single training run. But this basic model of repetition is one that can be applied to almost any type of data, and it's particularly suitable for the kinds of recognition tasks or the kind of synthesis tasks that really have no closed form solution. And the recognition of Tibetan mastiffs is a hard one to reduce to a single equation. You just can't tell the programmer, oh, here's a bunch of pictures, write me the formula which describes Tibetan mastiffs. You really almost have to fall back on this kind of statistical approximation that's at the essence of machine learning models. But we can use that same thing across so many different data types, whether it's images or video sequences or voice or written language or financial transactions. Almost any complex data set or real-time stream is suitable, and we can extract almost any identifiable property of that if we're willing to find a way to label that data. So what we find is that it applies in toy problems, like toy dogs, but it really is having an important impact across a range of different kinds of functions, particularly around vision and speech and language, where the kinds of vision functions that dominate are things like object recognition, scene segmentation, face recognition, pose estimation, resolution enhancement, and where we then take those things and apply them to security and surveillance, or autonomous vehicles, or advanced driver assistance, or to marketing analytics, or to user interfaces. And it's important to keep in mind the functionality of the individual functions and how it can potentially map to the applications. Similarly, in speech and language, we have recognition, we have enhancement, we have parsing, we have speech synthesis, and other kinds of speech analytics are emerging. Identity, demographics, emotion, location, all kinds of information is encoded there. And it applies, of course, across telephony and video production and user interfaces. Let's look for a moment deep inside the computation, because that's going to start to tell us important things about what's happening at the silicon level. So really, fundamentally inside these models is a layer cake of linear functions, sum of products, where at any given layer, we're going to take some inputs. For example, the initial inputs are x, multiply them by a set of coefficients, and sum them up with a bias factor. And then we apply some nonlinear function, which has a triggering property to it. And then we take those intermediate results and rinse and repeat. We do the same thing, multiplying by coefficients, adding a bias, summing them up, adding a bias, applying a nonlinear function. And then we go through all of these layers. And it's called deep learning simply because the layer cake of these, this stack of linear functions and nonlinear functions is often quite deep. Tens or even hundreds of layers with literally often millions of coefficients and billions of multiplies to be performed. And so when we look at the scale of computation associated with it, per evaluation of a model, you may have anywhere from 10 to the 5th to 10 to the 11th multiplies per evaluation. And then depending on the application and the data type, sort of the frame rate or the block rate or the sample rate, you will have a certain number of evaluations per second that you need to do. When you're training, you do the evaluation and then you do backpropagation to adjust to those coefficients. Once you have trained a model, you only work in the forward direction. You take the inputs, you use the now fixed coefficients to evaluate the output, finally getting to some output. And that output might be a waveform. That output might be a one-hot encoding of where are the Tibetan mastiffs in my image. It could be where my pedestrians, whose face is that, lots of different possible output functions. The memory is really dictated by the size of the model, how many coefficients are used, and what's the size of all of that intermediate storage, which is in some ways related to the size of these layers. The intermediate results are often larger than the size of the coefficients. That's particularly true in some kinds of convolutional neural networks. But interestingly, the code size for these applications is typically quite small, at least for the neural network itself. But it highlights one of the really important engineering issues associated with deep learning, is that we tend to fixate a little bit on the deep learning evaluation itself, as if it were the whole problem. And it's true that it often represents 99% of the computational horsepower. But as an engineering task, the pre-processing of the data, the capture, the manipulation of it into the proper form, the post-processing to filter the outputs and use the outputs is often much larger. You kind of have a 99-1 rule that tends to emerge, where you may find that the deep learning model represents 99% of the compute, but only 1% of the lines of code in the application. And this shows up as these neural network systems are coming to market, in that the software development, the system development is often only partly limited by the availability of the neural network engines. It's much more often limited by all of the other software engineering tasks that surround it. So let's look a little bit about what the implications are for the silicon structures themselves. So at the heart of evaluation is often this n-dimensional convolutional process. And I'll talk to convolutional neural networks especially because they're so much the foundation of vision processing. And vision processing, because of its high computational load, really is at the heart of the motivation for custom silicon. But it's also true across other kinds of tasks. Convolutional neural networks are used even in speech processing and in other kinds of processing where you're looking for patterns across large data sets. But fundamentally, we have, at any one level in that network, we have typically, let's say, a three-dimensional matrix of results. If this were an audio problem, you might have one dimension being the time dimension, one dimension being the frequency dimension, and the third dimension is a set of feature maps. That is, a set of intermediate results that come from prior layers computation. And so when we perform a convolution, we're going to take one of these filters. Those are 3 by 3 by 8 filters. And we're going to evaluate that filter at every offset in these two dimensions, t and f. So it does a multiply of a coefficient times a data value and sums it with the whole volume of that filter coefficient. And that becomes that convolution, that 3 by 3 by 8 in this case, becomes one data value, which contributes to a new feature map in the output. And similarly, we will have other filters. Remember, these filters have all been automatically generated in the training process. And each one of those convolutions, again applied at every offset in T and F here, becomes another layer. And then we take that whole structure and it becomes the input to a new layer, and we apply a whole nother set of filter coefficients. So what are the implications in terms of silicon structures? First of all, there's enormous parallelism here. You have the parallelism of the different filters, you have the parallelism for the multiply across the different feature maps, you even have parallelism across the evaluation in a single layer. And you may have multiple inputs coming through, and so this whole structure may be parallelized across in at least 5 different dimensions that I can think of off the top of my head. And so this is a VLSI designer's dream because there's so much latent parallelism. And at least in the case of some classes of neural networks, specifically convolutional neural networks, you get to reuse the coefficients at least very heavily, because I was sliding this set of coefficients, so I was using each coefficient potentially tens or hundreds of times for each load of a coefficient. So in some cases, it's also very memory efficient. And that helps make it possible to throw more VLSI resources at it and actually get significant kind of linear scaling in the amount of VLSI that I throw at the problem. And of course, what you find then is people design big engines that may do 10 to the 5th or 10 to the 6th multiplies per cycle on a single chip. And we'll continue to see that grow. Obviously, though, as you push even more multiplies through, you will eventually run into memory bottlenecks. And so people are coming up with a wide range of clever mechanisms of embedding memory in the devices, of having very wide memory paths, of distributing engines with some amount of local memory across these nodes in order to overcome those memory conditions. What you typically will find is there's some kind of local memory which can hold a subset of the coefficients and data and accumulators for maximum reuse. And there is locality in this as you do kind of regional computation here. As the models get really big, though, as the total volume here gets big, or as you do models such as recurrent neural networks or fully connected neural networks, which do not have as much coefficient reuse, you may be pushing the envelope on off-chip bandwidth as well. And so memory architectures that can provide the necessary bandwidth are going to be at a premium. Part of the good news, though, is that unlike general purpose computing, where there's data-dependent computation, which means that there's data-dependent memory reference, the access pattern is completely predictable. You know days beforehand what is the exact sequence of addresses that need to be fetched. And so there's significant cleverness that can be applied in algorithmic prefetch in these architectures in order to make sure that the data you want, even if it comes from far away off chip, or even from another subsystem in a large-scale system, can arrive just in time, so that the amount of buffering that you require is modest, and you're not necessarily very dependent on the latency of memory reference in these, because you can fetch ahead. People, of course, have applied a wide variety of different architectures and VLSI structures to doing the computational part of it. And I would basically break down the kind of computational structures into 4 categories. One, you can have a very dedicated engine that sort of has in its state machines this whole process of applying this kernel of computation to this block of data, and it really sequences a set of multiply and memory resources to do that thing. Not very smart or flexible, but attached to a CPU, which is really the brains of the operation and which is controlling that dedicated VLSI, often fairly monolithic lump. You have processor approaches that typically exploit wide SIMD, and wide SIMD can mean thousands and thousands of bits wide. And we see DSPs and vision processors and other quite programmable processors that rely on wide SIMD to provide the memory bandwidth and the computational bandwidth. There is an emerging category of coarse-grained reconfigurable arrays. These are, in a sense, cousins of FPGAs in that the interconnect between them is programmable in a sense, and where there is a node with a modest number of computing resources and typically communicating in a primarily nearest neighbor fashion with the other computing nodes. I think that the high-profile startup Samba Nova is a good example of this category. And then there are a class of things that fit somewhere in between the SIMD processor and the reconfigurable array, which is fairly autonomous computing engines, each of which is programmable, but instantiated in very large numbers, thousands to tens of thousands of nodes per chip. And you can put almost any of these architectures into that quickie taxonomy to understand it. But before we talk about the startups themselves, it's really useful to look at what the applications are that are driving this. And this is some data from Tractica. And this is their estimate. So this is $10 billion, $20 billion, $30 billion, $40 billion of software revenue associated with AI. And it gives us a sense of what the leading applications are. So the voice and speech recognition, video surveillance, network IT operations management and marketing, customer service, machine and vehicular object detection, personalized tutoring and adaptive learning, and so on down the list. And we note here that several of them are substantially edge-based, not exclusively, because speech recognition is something that happens both at the edge and in the cloud, but where there are ample reasons to expect that it will naturally migrate to the edge, because that's where the voice is originating, or that's where the video is being captured for surveillance. For something like network IT operations, it makes no sense to think of that happening at the edge, because it's fundamentally a cloud operation. But you can see that a number of the really high value software applications are also things that happen at the edge and have really significant hardware volume as well. In particular, speech recognition, video surveillance, and autonomous vehicles and advanced driver assistance. So this rapidly emerging, rapid in the sense that a lot has happened in the last 3 or 4 years, not just since last quarter, is turning into significant enthusiasm about representing these computational solutions at the level of silicon. So I've been tracking, who's doing what. And this is a combination of analysis that I've done over the last few years. Carl Schuler at Arteris also has been tracking this, and I merged our two lists together and researched all of these companies a little bit to really sort out which ones are true. It's truly doing deep learning startup chips. In some cases, a little hard to tell, because for example, in China, it's actually popular to say, I'm doing a deep learning chip, even when really it's a partnership with somebody else, because that is seen as a very attractive feature if you're raising money, that you're doing deep learning silicon. In US venture markets, the conventional wisdom, at least until recently, has been stay away from doing chips, and don't tell me you're doing chips, because it means that you're going to spend way too much money. And so people not only shy away from investing in silicon as a broad rule, but even if they're doing something in that area, they may downplay it if it's part of a larger system effort. And so you have these different attitudes, and there's a little bit more sorting out. Relative to the list I published last year in a talk here, we've seen 4 exits. Either companies got bought, like DeepFi, or companies that don't seem to have been able to progress. 4 companies that are off the list, and 16 that have been added. So there continues to be an acceleration in the investment here. And I've broken this down into, first of all, 4 large groups. Big system companies that are investing in doing their own deep learning chips. I've listed a set of the established chip companies. I'm not certain that this is exhaustive, but it's a pretty good indication of just how broad the conventional chip suppliers have been in incorporating deep learning into their architectures. There's a surprisingly wide variety of IP suppliers here. So clearly, all of these IP suppliers believe either in startups or in established system or chip companies, there's a lot of opportunity. And I really can't guarantee that I've captured all of the established system companies that are doing this. But the chip companies are the largest group by far, and it's very diverse. First of all, it's geographically diverse. I've tried to give a little bit of a sense of where they are. So the blue text means companies operating primarily in Asia. The green is primarily Europe or EMEA, and black is in North America. So you've got a pretty broad distribution. Now, of course, we live in interesting times when it comes to tech investment in different parts of the world, and the current US-China trade war may have some effect on this. In fact, I would tend to guess that it will accelerate investment in chip design in China as Chinese supply chain tries to make itself less dependent on US suppliers. And it may dampen the investment in the US because of a smaller market as a result. So this trade war may in fact turn out to be quite good in some abstract sense for chip development in China at the cost of chip development elsewhere in the world. We'll see. We can also look at this another way. And I think this is an important way to understand what is the diversity of the market that we're talking about. So I've attempted, to the best of my ability, to sort all of these 35 startups on two axes. So the vertical axis is the degree of specialization. At the top of it are people who are building fairly general purpose computing platform, but which happens to include deep learning as one of the things that it's good for. You tend to find that architectures that do both inference and training will tend to be pretty high on this list, because training is a more complex application. It tends to be something where you need higher levels of programmability, higher levels of generality in the data types and the operations in that computing engine. Whereas when you move to things that are highly specialized for deep learning, they tend to be highly specialized for inference, which really is just evaluating the layer cake, really focused on doing those multiplies and adds with the smallest amount of data movement and the smallest amount of energy in the smallest piece of silicon possible. The other axis is really where in the system, where in the network it is intended to live. From cloud systems, which tend to be very highly scalable, they dissipate lots of power, they tend to have lots of memory bandwidth, and they're built for connectivity with the other high-performance computing capabilities that you see around the cloud. And way at the other end, you find the ultra-low power applications, where people are talking about doing serious machine learning in hundreds of microwatts. And so this range here not only is sort of edge to cloud, or ultra mobile to ultra fixed in place, but it also represents a continuum of power levels. You could almost break that up and sort of say, here are things that run in hundreds of microwatts, in milliwatts, tens of milliwatts, hundreds of milliwatts, watts, tens of watts, and hundreds of watts. Because there really is 6 orders of magnitude in energy per chip, power per chip, associated with this range of different platforms. So it's a huge distribution. If we kind of take a step back, you will tend to see relatively more of the Asian chips distributed here into the low-cost domain. Not a big surprise. Because the Asian supply chain tends to be a little bit more consumer-oriented. You see a little bit more black up there because the US supply chain tends to be a little bit more cloud-centric on the average. And so you see some amount of separation in this broad distribution. Now, not everything is on sort of the line that says that cloud systems are all general purpose computing and low-cost systems are also very specialized to inference, but it is a good overall trend. I think it's interesting to look at some of the outliers which have gone for relatively more generality, even generality in relatively low power, low cost devices, or things that have gone for quite a bit more cloud centricity, even while focusing primarily on inference. So now I want to take you through a couple of concrete application examples. So looking at some real products and platforms that have been built specifically to address some of these high volume applications. So the first one I'm taking from the company Algolux, and they're building a unique deep learning based automotive perception system. And the thing that's kind of most interesting about it is that they, in their EOS perception system, they throw out virtually all of the pre-processing. They virtually throw out all of the image signal processing, which has evolved over the last couple of decades and which is a staple of any kind of a vision system today, and replaced it with a completely learned neural network system. And the result is that they are able to detect objects at much lower light levels or under much more severe glare conditions than conventional systems. But it is a significant computational investment if you look at the, kind of the categories that they consider. You're talking about things where they have applications aimed at processing engines like Intel Movidius, at NVIDIA TX2 and NVIDIA Drive. So we're talking about things from hundreds of milliwatts to hundreds of watts. And so there is room for a range of solutions in different platforms. But it's also clear that volume goes up, probably exponentially, inversely exponentially in power. So that you need to go to low power to get to the cost points, to get to the high volume distribution of high volume deployment of these. And actually, I would expect even in autonomous vehicle, outside of the autonomous taxi segment, which is emerging as a little bit of a separate beast, that we're going to see significant cost pressures even in these very sophisticated automotive systems over time, so that we expect that we ultimately land in the watts to maybe tens of watts as solutions here. And so there's a little bit of a video here to give you a sense of the relatively better rate of object detection here compared to the baseline system here. This is actually finding, I think, 2 or 3 times as many objects. And that's actually really significant, because if you think of a missed object is essentially a potential fatality. So the number of missed objects per kilometer is a really pretty serious indicator of the opportunity for improvement in these automotive systems. And then I'll take my favorite topic these days, which is speech. The fundamental problem with speech is that we do not live in our quiet living rooms. We do not live in environments which are fundamentally serene. We go to trade shows, we go to restaurants, we go outside, we drive our cars, and the level of noise there interferes with speech. It interferes with human-to-human communication. It interferes with any hope of doing very robust speech recognition for user interface or other services. And just to give you an idea here, I've just taken 2 examples, one under quite quiet conditions, where the signal-to-noise ratio is very high. Big signal-to-noise means quiet. So let me just give you a little snippet here. Hey, Gabby, turn down music. So, and you can see in the spectrogram here, which is time versus frequency, that you can really pick out that whole harmonic structure of the human voice. And you've got this distinctiveness in the start and end of phonemes and words. On the other hand, when I turn up the noise, it becomes much more difficult. Hey, Gabby, turn down music. So the human ear and brain are pretty well attuned, and most of you probably got that. But we often operate in environments that are even worse than that. It's routine in this kind of environment that you might be at -5 or even -10 dB, where the sound is really lost. And there are lots of applications in mobile calls and video conferencing and all kinds of mission-critical communications. So there are significant computing opportunities and implications here. Babel Labs is doing some quite remarkable speech enhancement. So taking noisy speech in, even from a single microphone, and producing clear speech out, subtracting out the noise, essentially by recognizing what is noise versus what is human speech. But to do that's pretty computationally intensive. To give you some order of magnitude results, we're doing roughly 1 million multiplies for each sample. We're sampling typically at 16 kilohertz, so each one of those is taking on the order of 1 million multiplies. And we're training models with, a small number of millions of coefficients. But one of the things about speech which makes it interesting and hard is that we have speech happening everywhere. It happens in the cloud, it happens in your phone, it happens in IoT devices, it happens in your car, it happens on your PC. It is almost universal as a desired interface for human-to-human or human-machine interaction. And so not only do we face the task of building these neural networks, but we also have to figure out, well, how do you actually map them onto GPUs and x86s and onto ARM and onto a whole range of different emerging neural network controllers. And so over the last year and a half, we've accumulated a remarkable set of scars as we've learned what is it that is going on in the emergence of this newfangled hardware. And I think there's some clear lessons about we have hard problems associated with the quality of the software tools associated with these novel neural network engines, that the integration of it into the rest of the platform, particularly into bare metal platforms, is really tricky, and that we're actually still at a very immature stage in the robustness of the software associated with all of these hardware. And as I've talked with all these different chip design companies, and I know the majority of them directly, I see a systematic problem that there is over-investment, relatively speaking, on getting the hardware right, and under-investment in getting the software tools right, without sufficient understanding of the end applications, without sufficient understanding of the diversity of things that people are going to do beyond the popular half-dozen networks that are used as benchmarks. But the result of using neural networks can be quite remarkable. Here's a little demo video showing 4 different languages of speech.
大家可以看到有很多水啊，我现在是在做一个语音智能测试，然后有很多水声啊，然后这里是很吵的。大家可以看到有很多水啊，我现在是在做一个语音智能测试，然后有很多水声啊，然后这里是很吵的。
أنا محمد، أنا أمام أهرامات الجيزة، أمام هرم خوفو الأكبر. نحن نجرب تكنولوجيا تحسين الكلام الجديدة في بابل لابس لنرى مدى نجاحها. إنه هرم خوفو الأكبر. أنا محمد، أنا أمام أهرامات الجيزة، أمام هرم خوفو الأكبر.
I don't speak Arabic, but he's talking about Babel Labs and being in Giza, so that's great.
لنرى مدى نجاحها. إنه هرم خوفو الأكبر.
トモです。今日は、キャンベルまで来ています。キャンベルのレストランでお昼を食べています。はい。トモです。今日は、キャンベルまで来ています。キャンベルのレストランでお昼を食べています。
Babel Labs offre piacevolissimi e intelligibilissimi audio e video, anche con questo casino! Babel Labs offre piacevolissimi e intelligibilissimi audio e video, anche con questo casino!
I'm in Beijing, China, to demonstrate clear cloud noise reduction. And I'm in Beijing, China, to demonstrate clear cloud noise reduction. So it really is quite remarkable what you can do in neural networks on things that are as complex and as intimate as speech. But this is the functions that we're now mapping onto specialized neural network engines to run in your phone, and this will be fairly ubiquitous in personal devices. So where does that take us? I think we can make a few generalizations to wrap up. First of all, the whole essence of the specification, the whole design of an application is rooted in having the right data to train the network. In fact, you could say that the labeled data is the application. The rest of it, the design of the neural network, the training, that's just kind of a compiler for the application, which is represented by the data. Second, it really is a new computing model. It sits alongside of the von Neumann, Turing, sequential execution, explicit state transformation model of computation, and is likely to persist, I think, for a long time as a co-equal element in the software world as a computing model. And the underlying hardware, therefore, is going to provide some co-equal support for both conventional sequential execution or algorithmic procedural execution and for these learned statistical models. Third, deep learning looks pretty different at the cloud and at the edge. In the cloud, you typically are talking about huge compute, often very memory intensive, often aggregating across data coming from lots of different sources, often very memory bandwidth intensive. At the edge, you may have high bandwidth, but you're typically operating on streams coming from an individual or a small set of local sensors, and where you really need to minimize power, minimize cost, minimize latency, and often maximize privacy to do it. Fourth, neural networks are inherently diverse because the applications they serve are inherently diverse. We got 6+ orders of magnitude in the level of compute, the level of power, the data rates associated with them. But it is going to be a building block in everything from hearable devices that operate for long periods of time on a battery charge, or even things that are embedded into stickers that get pasted onto things, all the way up to supercomputing class clusters. And finally, there is a corresponding shift in software methods as we add this network development alongside of code development as part of the fundamentals. And in fact, when we think about the impact at the chip level, we will certainly see deep learning engines appear all over the place, or deep learning motivated extensions to architectures. But it is really in the overall system design flow from silicon out to application deployment that will be driven increasingly by these considerations of these learned statistical models. So yes, the chip design structure will change, but more importantly, the design methodologies will evolve as we figure out what does it mean to do verification on some of these new kinds of structures, or what does it mean to do hardware-software integration when software means something different than it meant before. What is the kind of security issues that come when we have more frequent updates and we're considering the statistical behavior of these systems. So the global impact is quite significant, even beyond the specific impact on chip real estate. So I want to thank you and hope there's time for a question or two. I think there's a microphone up here.
So in terms of the speech enhancement that you showed, removing noise, currently DSP techniques do it and do it fairly well, my Bose noise cancelling headphones do pretty well. So what's the advantage of Babel Labs over something like that?
It's true that there are DSP methods that work to filter the noise. The big difference is what amount of noise and what variety of noise can be removed. The adaptive filter methods that dominate classical DSP methods are typically work best in stationary noise. That is sort of the fan noise that is constant. If you have something which is rapidly changing, a gunshot, for example, it's very difficult for an adaptive filter to understand how to deal with that. So it's really quite limited in the amount of noise reduction that it can perform in those more difficult conditions. I think there also are some classical methods like multi-microphone methods. In fact, a lot of the progress in the last 10 years in noise reduction has come from that sort of microphone triangulation. And that's actually orthogonal to this. You can put the two of them together and you get the sum of it. So to make it more explicit, a really good multi-microphone noise filtering method might remove 4 or 5 dB of noise. This by itself from a single microphone may remove 10 dB of noise. So the combination may be 12 or 15 dB of noise reduction from a combination of things. If you apply the whole toolkit of capabilities, sometimes the combination will remove more than 30 dB of noise, which is a 1,000x reduction in noise, which is unprecedented by classical methods.
Hi, Chris. Nice to see
Hi.
you again. I have a question for the two examples you show, right? The first one is the company about the video recognition. They basically get rid of all the pre-processing in the image detection. But in the Bubble Lab example, do you do audio processing before the AI processing?
Yeah, so the question is really, in the Algolux example, part of the breakthrough was to replace the conventional DSP processing with deep learning. What's the analogous approach in the Babel Labs case? Probably the closest analogy there would be not our speech enhancement, but the work we're doing in speech recognition. Because there, conventionally, you have some noise reduction, and then you have a speech recognizer. In fact, when we build a speech recognizer, we build the noise reduction, the noise tolerance into the neural network itself. So it's trained for noise tolerance. And in fact, even if you look at the speech enhancement case, we really have minimal pre-processing. In some cases, we may move things into the spectral domain, so there may be an FFT in there, but there's really not significant prior processing. It's a little bit more complicated when we get to the case where we combine deep learning with multi-microphone, and so we're doing a sort of deep learning beamforming method that essentially subsumes the two functions together. But I think the theme holds that, in fact, some of the conventional DSP, much of the conventional DSP, is either being replaced by or incorporated into a learned function in the neural network.
Yeah, so actually that's exactly the question I want to be more specific, is whether you do beamforming and adaptive filtering beforehand, and your answer is
His answer is no, we don't do it
Thank you.
beforehand. Yeah.
Thank you.
All right. All right, well, thank you very much.